Okay, it gives me great pleasure to introduce today's speaker, Andreas Blass, with whom I had the distinct honor of sharing an office at the Newton Institute in the fall of 2015. Andreas is, of course, of the University of Michigan, and he will speak to us today about choice from finite sets, a topos view.
Thank you. Thank you for inviting me to speak here. Okay, so what I want to do is explain connections between choice axioms for choosing elements from each of a family of finite sets and some topos theory. And in a set theory seminar like this, I realize I'm going to have to explain topos theory. And in fact, a very large proportion of my slides are headed with either introduction or preliminaries, and the proofs of theorem sort of got squished to the very end. And well, if I talk fast enough, I might get to them, but we'll see. So let me start with some set theory. Choice from finite sets. So I'm talking about a family for non-trivial situations, an infinite family of finite sets. And the question is there a choice function? And the subject begins, at least the part that I want to talk about, begins, oh yes, of course, we're working in set theory without the axiom of choice, so that there is something non-trivial instead. The subject begins with a result of Tarski, I think at some point in the 1920s. He never actually published this, but he proved it anyway. Here it is. If you can choose, you can have the axiom of choice for two element sets. So given any family of pairs, there's a choice function. Then you automatically get choice from any family of four element sets. The converse is extremely easy. If you have choice from four element sets, you can turn any two element set into four by taking product with the number two, choose from those, and then project to one of the original elements. But knowing how to choose from two element sets does not obviously give you a choice from four element sets. Let me, it's not on the slide, but I think I will wave my hands at Tarski's argument for this. So supposing somebody gives me a bunch of four element sets, and I know how to choose from two element sets. And I'm going to wave my hands as though these four element sets are disjoint, which they are without logic. In each of those four element sets, what I want to do is take all the two element subsets of that four element set, there are six of them, and choose from all six of those in every one of the given four element sets. So each four element set now has six choices made in it. Of course, some element, if you're going to choose six times from a set of four, you're going to have some elements chosen more than once. So elements get chosen with various multiplicities, but notice that they can't all be chosen the same number of times because four doesn't divide six. Am I inaudible now? Let me get back to turning up my volume.
We can hear you.
Better?
We do hear you. It's fine.
Okay, it will get bad again. In fact, it's already starting to drift downward. Okay. I hope it's okay. Can everybody see and or hear me? I'll try and wave my hands vigorously so that you get something you can't hear. Thank you, Gordon. So within each of these four element sets, you've picked from each pair. Some elements have been picked more often than others because four doesn't divide six. Look at how often each element is picked. Look at the elements that are picked the most often. If there's only one, that gives you a way to choose that element from the original four element set. If three of them are tied for best, then choose the other one. Right? The only other possibility is that two of them are tied for best, the two are tied for worst. Take the two that are tied for best. You've already chosen one from that pair. There's your choice from the four elements. Okay, so hold on just a second. I'm going to move this so I get to the volume adjustment if I need it again. I've got some notation here on the slide. CIN choice from I-indexed families of n-element sets. I believe I'm using the same notation here as in the book of Paul Howard and Gene Rubin on consequences of the axiom of choice. So Tarski's theorem can be written this way: if choice from pairs for all possible index sets, that's this part, then you also have choice from four element sets for all possible index sets. Notice that this is not the same, and we are not claiming that for each index set individually, choice from that many pairs implies choice from that many four element sets. Good reason for not claiming that is that it's false. It's false even if I is omega. In other words, if you have choice from countably many pairs, you do not necessarily get choice from countably many four element sets. That was a little suspicious given my proof. If I had countably many of those four element sets, and then I take the two element subsets of them, at first sight it looks like I've got countably many times 6. So it's still countable, isn't it? Yeah, countably many times 6 is countable, but just having those 6 two-element subsets in each four-element set does not guarantee that you've got countably many. If you want to count those pairs that you're choosing from, you have to make an ordering in which to choose them within each four-element block. It may not exist. Okay? So to prove, I guess what Tusky really showed is that if you want to prove choice for I-indexed families of four-element sets, you need to use choice not for I-indexed family pairs, but for J-indexed families, where J is a little bit bigger than I. J has a 6-to-1 map onto I. So, and in fact, it's not just that Tarski's proof doesn't work. If you restrict to countable families, it is in fact not provable in ZF. If I had infinitely much time, I'd tell you a nice, at least the Frankel-Mostovsky counter model, and then mumble something about transferring the result to ZF. But I don't have infinitely much time, so I'll just say that implication is not provable. On the other hand, you do have the countable version, and in fact, the I-index version for any fixed I working, if you assume choice from pairs and choice from triples, then you do get choice from four element sets. Now that deserves another hand wave. I think this is also due to Tusky, but I don't actually know for sure. It's actually easier than the previous one. If I'm given four element sets, what I do is in each four element set, consider ways to partition it into 2 plus 2. There are 3 ways to do that. This way, and I can't do it well with my hands, but diagonally. It works better if you draw the 4 elements as a triangle in the center of the triangle. And one partition is that pair, and the other 2 partitions are done by rotating the triangle. So each of the 4 element sets has 3 partitions into 2 plus 2. Choose from that batch of triples. In each 4 element set, choose one of the 3 partitions. So now you've got 4 element sets, but each one is already partitioned into 2 plus 2. Now use choice from pairs to pick one of the 2 pieces in each 4 element set. Now you've got a 2 element piece picked out. use choice from pairs again to pick one of the two elements. That picks out one of the four original elements. So we do have this, what I call the local version of the implication, if you assume both pairs and triples. Local in the sense that it works for each index set I individually, whereas what Tarski's original theorem was a global theorem, assume choice from pairs for all index sets. Then you get choice from quadruples for all index sets. Somewhat later, 1937, I think is the date of publication, Mostovsky did a general study of implications between finite choice action, choice from this many and this many and this many implies choice from that many. He also gave a proof of Tarski's theorem, with proper credit to Tarski, of course. In fine print, it's really a strange thing. You're reading this paper, it's in Fundamenta. Read this paper, and all of a sudden it goes into what looks like footnote-sized print, but it's in the middle of the page, and it's essentially presenting Tarski's proof that I just outlined at the beginning of the talk. So this is, as far as I know, this is the first publication of Tarski's result. This simplifying notation, I'll write C of I Z for a finite set Z of integers to just mean the conjunction of all those individual C of I single number. So this C of I Z means choice from an I index family of sets whose size is in Z. Maybe I should say something careful about this. Suppose I have an I-indexed family of sets which have different sizes, but all the individual sizes are in Z. That will also have a choice function if I have C of IZ, because I can essentially get a choice function for each individual Z, and then because Z was finite, I can get one such function for each little Z and put them all together. That's the main reason for having finite here. The definition would make sense for infinite Z, but then you have to be careful am I saying this only when all the sets have the same size or when they're allowed to have different sizes. And it matters. So this theorem that I had up here would, in this notation, be written this way. For each individual index set, choice for pairs and triples on that index set implies choice from quadruples on that index. Okay, so what did Mostovsky do? I would say the question that he was addressing is, when do you get an implication of this sort? When does a finite batch of these choice activities imply another one? This is the version that corresponds to the original Tarski theorem. There's the stronger version that has it working for each index set I individual. So as I said before, I tend to call this first version the global version and the second version the local version. I think it's time to increase my volume again before it gets too bad. So Mostovsky provided some necessary conditions and some sufficient conditions for provability of such implications. He didn't quite get necessary and sufficient conditions. So there are necessary and there are sufficient ones, and in many cases they suffice to decide whether an implication works or not, but there were still some gaps between them. Technically, I think he got conditions primarily for the global version, the first of these. Turns out the second kind is actually easier, but I don't remember whether he got any of those. He may have looked specifically at the case of countable index set, countable choice with Z-size sets, implying countable choice with N size. were not resolved by his, he had some general theorems, and then he did specific computations for particular z's and n's. The first case that he couldn't resolve was this: if you assume that all families of 3-element or 5-element or 13-element sets have choice functions, will there always be a choice function for a family of 15-element sets? It was, I think, known for quite some time as the 3, 5, 13, 15 problem. Okay, that was Mostovsky in the 1930s. Now we zoom ahead to Gaunt in 1970. He answered the global question, so he sort of completed Mostovsky's work on that, and essentially answered the local question. I'm not sure he phrased it exactly that way, but he had criteria for when choice from countably many Z-sized sets implies choice from countably many N-sized sets. So he had it for the case where I, in my formulation, is omega, but in fact, the general case is very similar to the countable case. So that's what I mean by essentially answered. But published only an abstract announcing the results. So as far as I know, Gaunt's publications had 2 abstracts. In those days, it was in the notices of the AMS. The first one in 1968 gave some partial results on these problems. In 1969, he completed his PhD thesis. He was a student of Carroll Carp at Maryland. In 1970, he published an abstract announcing the complete solution. And as far as I know, never published anything more about the complete solution. Fortunately, 2 years later, John Truss published a paper in one of the early issues of the Annals of Mathematical Logic, giving Gaunt's results with proofs and considerable extensions of them. Maybe I should say something about considerable extent. How do you considerably extend complete results? Truss also looked at questions like, what happens if instead of just knowing the cardinality of these sets, you know something about their structure? You might look at axioms, choice axioms, for instance, of the form, given a family of 4-element sets, each with a specified cyclic ordering, and you then get choice functions. Or given a family of 15-element sets, just to pick a 15 at random previous slide, can you always choose for each of these sets a partition into a subset of size 7 and a subset of size 8? You can imagine lots of these given sets of not just a certain size, but with a certain structure on them. Can you produce either elements, as in an ordinary choice function, or some other species of structure on these sets? And Truss's paper gives answers to, I think, in fact, all questions of that sort. So here's Gaunt's theorem about the local implications between choice functions. This really should have some parentheses. The if and only if is the main connective here, not the ZF proves. So ZF proves the implication. If and only if all this other stuff holds. Not ZF proves that the implication is equivalent to that. So what is all this other stuff that I've got highlighted in green? Well, it's an entirely finitary criterion, unlike axiom of choice, which is about all kinds of infinite families. And the criterion is a combinatorial one. It says if I've got a finite group acting on an n-element set with N is this thing. I've got a finite group acting on an n element set without fixed point. What's a fixed point? It's an element of this set that is fixed by everything in the group. I'm not requiring that every element of the group moves stuff, but every element of the set could be moved by at least one of the group elements. Maybe I should just be very careful and make sure that we're on the same page with regard to the notion of acting. Say that a group acts on a set, just to say we assign to each group element a permutation of that set in such a way that composition of permutations corresponds to the multiplication operation of the group. In other words, a homomorphism from G to the group of permutations of that set. If G acts without fixed points on an n element set, then the way it's stated by Gaunt and I think also Truss and Akintold is that there should be proper subgroups whose indices means the number of cosets in the case of I in G. Indices add up to an element of set Z. Okay. These subgroups, as I said here, not necessarily distinct, not necessarily non-trivial, but they do have to be proper subgroups. They can't be equal to each. A better way, in my opinion, to think about that requirement on the indices of these groups is to say G acts without fixed points on a set whose cardinality is in Z. The point is that for any individual case of I, G acts on the cosets of case of I, acts on the cosets of any subgroup, by just multiplying from the left. Coset X times case of I, an element of the group, say little g, acts on it by little g times X times case of I. So these indices can be thought of as the size of an orbix, a set on which G acts essentially by left multiplication of cosets. And having a sum of those things in Z is to say that I can have several of those sets, G acting on each of them, and the total size of all of those, the union, is in Z. And the without fixed points part down here corresponds exactly to the proper subgroups here. Action of G on the cosets of the subgroup has no fixed points, if and only if the subgroup isn't all of G. The reason I prefer this formulation of the last part of the theorem is simply that it makes it look very similar to the hypothesis. A finite group acts on n elements without fixed points. Then it also acts on some number in Z of elements without fixed points. Okay. I am hearing some background noise that is coming from my computer and not from me. I think that's what's causing the my sound to randomly die. It stopped for a moment, but it's back. In any case, more introduction. Kant's answer. Here's Kant's global theorem. It's very similar to the local theorem, but if and only if characterizes when Z proves, but now this is the global implication. Choice from all T size sets gives you choice from any n size. So this is the global implication, which remember is weaker than the local one. And as a result, this condition is also weaker and regrettably longer, but I only have to put up with that. It It begins the same way. Whenever a finite group P acts on an n-element set without fixed points, then, and the ending is the same also, proper subgroups whose indices add up to an element of Z. But the middle is different. In the previous slide, it was G itself has those subgroups whose indices add up to an element of Z. Now it's some subgroup of H of G has further subgroups, the K, whose indices in H add up to an element of Z, or in my third formulation, G has a subgroup H that acts without fixed points on a set whose size is in G. Okay. One consequence is that CF does not prove the implication. First implication that Slavsky left over, the 3, 5, 13 to 15 implication, because it turns out that there is a group that can act on a 15-element set without fixed points, but neither that group nor any subgroup of it can act on a 3-element set or a 5-element set or a 13-element set without fixed points. I don't recall seeing that group exhibited in any of the work that I've looked at. So one day when I had nothing better to do, I looked for it. And there is the counterexample group is a group of order 56. It's a subgroup of affine transformations with a 3-dimensional vector space over a 2-element field. That's an 8-element vector space. And I think Mustovsky must have known about this group. Otherwise, he wouldn't have singled out this problem all its unsolved games. But I don't think he said what the group was. Okay, so in any case, there is this funny group.
Sorry, wait, can I just ask a question before you move on from this slide?
Okay.
I'm still sort of digesting this condition about the groups with n-element sets without fixed points. But I mean, obviously, if choice holds, then
right.
Is it obvious under choice that you have all of these groups and that you can always do this?
Yeah, I mean, the existence of a group like this is just a matter of finite combinatorics. It's a group. So that doesn't care whether you have choice or not. But the issue is that this criterion, this thing, is not a criterion for when the implication holds. It's a criterion for when CF proves the implication.
Oh, I see. Okay, yeah,
So
thank you.
let me emphasize that in this theorem, the main connective is the if and only if, not the ZF proofs. It's not that ZF proves this humongous if and only if statement. ZF proves this one line, the implication.
I see. Okay, yes, that makes more sense. But
Okay?
I mean, this is almost. I mean, this is a statement of arithmetic, almost in a certain sense. Assuming I is arithmetic, I guess.
Yeah, the part after the if and only if is an arithmetic statement, I guess, I01.
Okay, thank you.
Okay. All right, so let me now say something about topos. And maybe I should ask first, are there other questions before I switch over to topos theory? Or at least topos hand waving or something. Okay. Topos theory it is. Okay, so this is not the definition, this is how you should think about a topos. Topos is a category, and it looks a lot like the category of sets, well, specifically sets and functions. So the objects are sets, morphisms between them are functions. And the axioms that will define what a topos is are essentially just saying that a lot of the constructions you can do with sets can also be done in these categories. In particular, similarity between a topos and the category of sets is sufficient to essentially do the beginnings of basic logic within a topos. We can talk about structures in a topos for the first order language. You can interpret first order formulas in such structures. And in fact, not only first order formulas, higher order as well, because the topos will have things that correspond to power sets in the traditional world of sets. Now, I need to say things a little bit more precisely than this, so let me give you a longer idea of what a topos looks like. I want to say something about how things get defined in categories. I said a moment ago, for instance, that a topos has something like a power set. What does that mean in a category? What do we mean? Essentially a power set, power object of some other object. In many cases, not all, I'll have some counterexamples in a moment, but in many cases, the definition, the way to transport a definition from the world of sets to the world of topos is to take the definition in sets, and it will say, okay, the object I'm constructing has the following elements that we traditionally define what a set is. We say what the elements in it are. In a topos, the right analog of that is not to try to say what the elements of an object are, partly because we don't really have a good notion of elements, but to talk instead about families of elements. Now, in the set world, a family of elements of a set X amounts to just the function from an index set into X. Categories can handle functions that become the morphism. And the idea is to just big sets, but try and say as much as possible in terms of families of elements and transport that into the category world. I think that's what I love. Speaking of functions of J into X, there's a J-indexed family of elements of X. And then take the usual set theoretic definition, and we're talking about what should happen with general elements, talk instead about general families of elements. I've written a couple of examples here. There are more, but okay, I want this talk to remain not only finite, but feasible. So, monomorphism, this is a fancy name for a one-to-one map. In sets, this is easy. F is one-to-one if for any two elements in X, if they have the same image, they were the same element to begin with. I'm going to say the same now for families. It's also true in the universe of sets that the criterion for F to be one-to-one is given any family, any two families of elements in X, if they have the same family as their image in Y, then they were in fact the same family to begin with. The version in terms of families gets transported to categories. There it is, given two J-indexed families, A and B, of elements of X. If they give the same family when you compose with F, and map them over to Y by F, then they were the same to begin with. So it's just the usual definition of one-to-one, generalized from elements, families of elements, and then written in terms of morphisms. That's what a monomorphism is. In fact, generally, in any category, we'll be interested in the case of a topos.
So there you vary J over all possible sets, or
Yeah.
over what?
Yeah. So this
Okay.
for all applies to A, B, and J.
Okay.
Yes, you need this for all of them, not just one or a few. Okay, subobject of Y. Let's here is an equivalence class of monomorphism. What's a subobject? Well, a subobject should be like a subset. And a subset does come with a monomorphism to Y, in which you have each element of the subset to itself, the identity map of that subset. In a category, we don't generally have a notion of one can be actually literally included in the other. So any one-to-one map of anything into Y should be regarded as defining subset, sub-object of Y. But then we have to be careful because another map of something else into Y could very well have the same image and should be thought of as the same sub-object. That's why we need to pick equivalence class. The equivalence has a fairly short definition, but I don't think I'll take time to do that. It's essentially giving a reasonable criteria for when you would expect to say that the images of two monomorphisms are the same subset. Let's see. Going on here, I'm asking when is an element of Y in one of these subobjects? No, I'm not saying that. I'm saying when is a family of elements? I wrote it here as element in quotes because I really want to think of these families to be in the category world the exact analog of what elements are in the set world. They're not exact analogs, they're for quotation marks. I'm going to call them elements. So an element of Y is in the sub-object given by some monomorphism Y. If that family can be gotten by taking a family in X and composing with a monomorphism. That's all this is. Okay, what else can we do here? More set theoretic constructions. A quote element, meaning really a family of a J-indexed family of elements in a product is a J-indexed family in the one factor and a J-indexed family in the other factor. I hope that wasn't my computer doing that. Get the volume back. This is just the familized version of the statement that an element in the product amounts to an element in the one factor and an element in the other factor. Maybe I should point out at this stage that there is a benefit, a very important benefit, doing definitions like this in terms of families of elements, mapping, morphisms, rather than just individual elements. And I guess the best place to think about that, the most familiar place, is probably topological space. That's not a topos, but it is a category. What I've been telling you here goes perfectly well there as well. If you define the product of two topological spaces this way, then a couple of things follow. First of all, the points in that product space are what you expect. Here is the points one would expect. But furthermore, this family's version of the definition automatically implies that you get the right topology, product topology on that product space. And furthermore, that continues even for infinite products. From an analogous definition of those, you will get the product topology, the usual Tikhonov product topology on an infinite product topology. Without having to go through this stuff that you usually have to convince to make a little bit of sense, where you think basic sets the products where all but finitely many of the factors are the whole space. It looks sort of like, okay, somebody tinkered with it until it finally worked. No, somebody tinkered with it just enough to make that definition work. That definition automatically gets finite. And it works for groups too. You get not only that the product of two in the category of groups, the product of groups has as elements what you would expect, element of one group paired with an element of the other group, and has the right multiplication operation, simply by virtue of this family approach. Probably an even better example, although a little bit further out in left field, if you like algebraic geometry, the product of two schemes does not have the points that you would expect, just point in the one, point in the other. More complicated than that, but the computation comes out automatically if you use this definition. Okay, back to topoi. Forget topological spaces and grouping schemes and all that. Those are yucky categories that we set theorists don't really need. Topoi are very like the category of sets. That's what I want to concentrate on. Okay. Let's see. I guess that new line there is just the case of a product of zero fractions of one element set. Each capital J, a map from J into 1 should amount to a zero tuple instead of a tuple. And there's only one zero tuple in the world, so there's a unique such map. I could define products of more factors, including infinitely many factors, exactly the same idea, but it turns out we don't need that for what I'm doing today. What's an element of the power set? Subset of X. What's a family of elements? J-index family of elements of power set. Imagine index set J horizontally and X vertically. A J-index family of subsets of X is each element of J is a subset of the vertical flavor over it. All of those together just constitute a subset of J cross X. And that's what I've written here. Family, a J-index family in the power set of X, subset of J cross X. That gets me a description of what a power set ought to be in any category. And in a topos, one of the requirements for a topos is that those power sets actually do exist there. Many other categories do not have power objects. Topoi do. What else? Oh, special case. Power set of a one-element set. We all know the power set of a one-element set consists of that set and the empty set. But it can get more complicated because from topoi, there could be more than just two values. Yes and no. Immediate things. This is sort of the beginning of where intuitionistic logic is going to sneak in on us. There is, I don't think I'll go into any more details of this, but just that we can describe inverse image of a subset with respect to a function in a very similar way. What else? Oh yes, now I said I have counterexamples. So far I've been talking about things like products and power sets and so on that can be described in terms of what are the maps into this thing, what are the families of elements. One of the nice things about category theory is that you actually dualize everything, reverse all the arrows, and see what you get. And sometimes you get garbage, and sometimes you get something reasonable. Whether it's garbage or reasonable depends on what category you're in. In the category of sets, here are a couple of, I guess, essentially one reasonable thing. No, two. I've turned around the arrows in the notion of a one-to-one map, and amazingly, it gives me the characterization of onto mapping. Fancy name epimorphism. You take you take onto, translate it into Greek as epi, bring it back into English and stick morphism on the end of it. That's where the terminology comes from. Onto maps are, in that sense, the dual of one-to-one maps. And a disjoint union of two sets. A map of a disjoint union into some other thing amounts to a map on this part together with a map on this part. Disjoint unions are the dual of product. So what you get, you take. What happened here? Oops, I don't want that yet. Take what I had at the top of the page for products, reverse arrows, and you get a description of disjoint unions, which are therefore often called co-products. All right. A topos, there are two real definitions of a topos. One is what I've written here. All the usual set theoretic constructions can be carried out and you make a humongous things. The other is all you really need is finite products and power sets. Everything else can be used from them. It's sort of like the idea of, if I were going to define for you what a field is in algebra, what I really mean by a field is that you can do all the algebraic stuff that you learned in 9th grade or whenever they taught you algebra, except inequalities. All the other rules of computation that you do with ordinary arithmetic, that long list of stuff, that's what a field really is about. But you can define it using just a relatively short list of things that are called the field axioms, and everything else follows. Same sort of thing here. The idea is you can do all the stuff that we normally do in set theory, not counting replacement. And a few other mumbles have to be put into that, but essentially the usual set theoretic constructions. But when you go to write down the axioms, all you have to say is finite products and power sets. One of the consequences of those axioms is that if you have any function from x to y, you can express it as first an onto map onto something, and then a one-to-one map. Essentially just a map onto the image of f, and then the inclusion of that image in y. So that R, that intermediate thing, is the image of f. Using that, you can define existential quantification. You have a subset of x cross y. Set defined by existentially quantifying it is just its image under a projection. Also define universal quantification. I've written it here as the largest B with certain properties. It takes some proof, the axiom of topos, to imply the existence of such a largest B, and they do. In fact, one of the early, I would say the first few years of topos theory were involved in sort of gradually chopping down more and more of the construction to finally get to this nice result that all you need is finite product powers. Just as another example of stuff that we usually do in logic can be done in a topos. Equality is a relation, a binary relation on X, so it should be some object of X cross X. And it's just a map into X plus X. Map into X plus X is a pair of maps into X itself. A pair of identity maps. Disentangle what all that means, and we'll find that, yeah, that is the identity relation. Oh yeah, any finite set or finite structure has a canonical copy in any topos, essentially because the finite set is just the disjoint union of a bunch of copies of one. And in a topos, you have the element one, the object one, and you can form disjoint unions. So that lets you build any finite set, and structures you can do similarly. I won't bother with the finite stuff in the real world has copies in any topos. That's the idea. Now I need to say something about internal logic. Let's see. Yeah, I remember this seminar usually is not too careful about ever stopping. I do plan to stop sometime, but it will not be immediate, I'm afraid. I do want to get to where I can state the theorem. Okay. So I said at the beginning, when I first started talking about topoi, they are the categories in which you can interpret first order and even higher order logic. Here goes a more careful statement of that. You give me a vocabulary sigma and I allow multi-sorted if necessary. It's not going to matter if we use single sorted in any of the usual traits. What's the sigma structure in a topos? Well, you want to have, what is it in sets? It's for each sort, you have a set, a domain of that sort. Now you have an object, domain of that sort. For function symbols, In sets, you have functions. Here you have morphisms. Predicate symbols in sets, you have a sub-object of the Cartesian product. Topos, you have sub-objects. This is sort of the unique natural thing to do. Not only that, but it works. First order formulas and terms can be interpreted in such a structure, essentially by transcribing the, for instance, you want to talk about the disjunction of two formulas, you need to form the union of the set realizing the one and the set realizing the other. But the union is just an image of a disjoint union under a certain map. Once you have images and disjoint unions, you form ordinary unions. I'm hiding a lot of preliminary work here because it's boring. Verifying that a lot of constructions can be done on the basis of topos axioms. Higher order formulas are also okay because we have power sets or power objects available. The one thing to be careful of, I alluded to that earlier with the truth values not being just yes and no. In a general topos, these interpretations make intuitionistic logic sound, but classical logic is not in general. It is in some topoi. If it is valid in a particular topos, we call that a Boolean topos. In general, we can't expect that. Also, to avoid having to put a lot of extra hypotheses on things, I'm going to talk about topoi that have what's called a natural number object. It corresponds to the topos, to a set of natural numbers. So it's like the axiom of infinity. Is this object of natural numbers? How do you define what object of natural numbers is? Real easy. If we have higher order formulas, we could say second order Peano axioms. That characterizes the natural numbers. Assume we have a structure that does that. There are neater and more category theoretic ways to say what a natural number object is without going all the way through this internal logic and setting up that machinery. But as long as I've mumbled something about the machinery, this is sort of the quickest way to say that I have a natural number object. Okay, we're finally done with introduction and up to preliminaries. Okay, relevant examples of topoi, relevant for the stuff that I want to put. Well, this is sort of to be expected. The category of sets and functions is a topos because we intended topoi to be sufficiently like this category, and the category is surely sufficiently like itself. Here's a more interesting one. Oh boy, but what noticing? Take a category of I-indexed family, fix an I, fix an index set, and look at families of sets indexed by that I. Such a family will be an object of this topos I'm describing. And a morphism from one such family to another will simply be for each index I, a function of set number I in one family, set number I in the other. I shouldn't say number, set index I, set index I in the other. So it's just basically a whole bunch of copies of the category of sets indexed by I, and they work independently of each other. There is a standard way in category theory and in some other branches of mathematics of thinking of an indexed family of sets. I wave my hands like this. Index set, x sub I, x sub j, x sub k, and so on. But I can also think of the disjoint union of all those x sub whatever, call that capital X, and it comes with a map. Each element in it came from one x sub I back into that I. So I'm looking at maps from whatever into I, And such a map represents the family of inverse images of points. I guess this is really F inverse of singleton I for being precise, but I guess I was not being precise when I wrote it. Morphisms, okay, technicality, what are the morphisms? The maps from X to the other X that commute with the projection, so they're mapping each X sub I into the corresponding X prime sub I, and not some other X prime sub J. Instead of taking honest to goodness sets and honest to goodness functions, I can take my favorite model of set theory. I can be pretty generous here. It doesn't have to be a well-founded model. It can be a model of with atoms. It doesn't even have to be VFs or Melo set theory is plenty good enough. You don't need replacement. I could do this with Boolean valued models. I would want to take the elements of the model and names for elements of the model and names which value one denote functions of the appropriate coordinate. That's why I think any model, if you do anything reasonable, it'll work. You can do the same construction up here, this thing. Maps are like this, like that. You can do that within any model M. Take an index set in M and look at families in M indexed by that. So the families, not only the sets in M, but the indexing is in M also. Another perfectly good topos. All of these things qualify simply because these things are all sufficiently similar to sets. It's like interpreting internal logic, meaning the interpretations of formulas in structures within these topoi. It's going to be just like what happened in sets or what happens within the model M of set theory. If you're doing things over an index set, it happens sort of independently in each fiber. In other words, nothing very interesting is happening here yet. In particular, you can write down a first order sentence as there are exactly n elements, right? There exists x1 through xn, not any two of them are equal, and for all y, disjunction of y equals one of those x. Say that as a first order sentence, and what it means when interpreted in the internal logic of the topos is that each fiber has exactly n elements in the usual sense of sets or model M. Here's the first place where things get interesting. A morphism from one, we're looking at M over I, so we're looking at I-indexed families of sets. One simply I-indexed family of singletons. Remember, each fiber works separately. A morphism from that into X is going to be in each fiber, the unique element of one gets mapped to something in X of I in that fiber. That's a choice function for the fiber. Morphisms from one into an index family is a choice function for that index family. Okay, more relevant examples of a different sort. Groups acting on sets. Well, fix a group and look at sets equipped with an action of that group. So the objects are sets with a specified action. And morphisms are functions that respect the action of G. In other words, if I have a function from this set to this one, and they both have actions of G, what's required for this function to be a morphism is if an element of G thought of as a permutation over here, then some element to some other element, then that same group element, that same element of the group must send the image of the first element to the image of the second. So mapping over, commute with commuting by group elements. written here, in fact, it's a Boolean topos. Oh, I should have said the ones on the previous slide are also Boolean. As long as I'm using classical set theory. Classical logic works in these things. Sub-objects are, not surprisingly, subsets closed under the action of the group. That way, the sub-object is itself a set with the group acting on it. The power set in topos is not just the set of those closed. It's a set of all subsets of X. Group acts on those subsets. Well, I've got a group acting on the set X, computing the elements there. It automatically acts on the subset by moving the element line. So the actual sub-objects are only those subsets in the power set that are actually fixed by the G action. One of the things that one needs to fix. And I've seen my volume paying again. I wrote down here because we'll need it in a little while. What does it mean for something in this topos to be an n-element set? It has a perhaps surprisingly simple meaning. It just means it has n elements. The way the group acts on it is irrelevant. So internal logic, when it asks, are there just n elements here? You have to do some work to calculate out what that means when interpreted. It turns out to mean simply that there are just n elements. And I also, as on the previous slide, added what is the morphism of one into some set with. Well, it's got to be a function. That's each element of one. There's something over here, but it's got to respect the G action. Any element of the group acts this thing to itself over his own. But when that is image to itself, you can fix the group action. This is starting to look promising. Previous slide, morphism from one to an object in model of set theory over I were choice functions. Morphisms from one to an object in G sets are fixed points. This is beginning to look like there might be some connection between the things involved in Gun's characterization of choice action. Oh, I have a slide here. Previous ones were relevant examples. Here are some irrelevant examples. They're here really only to emphasize that there are lots more topoi, especially because the relevant ones are Boolean. Here's a non-Boolean one. Instead of letting a group act on a set, let a monoid act. The monoid isn't a group. This will not be Boolean. If you really want to get away from classical logic and go intuitionistic, crypty structures are also objects of a topos. Or generally, pre-sheets on any small category. You don't need pre-sheets to go to sheaves on topological spaces or really into algebraic geometry, any sites. There are topoi in which the internal logic corresponds to various forms of realizability in proof theory. There's some set theory talk. Let me not do this in any generality. Suppose V equals L. Do some Boolean extension. And look at the ordinal definable things, not hereditarily ordinal definable, just ordinal definable in that extension. That they constitute a topos, and it has some rather interesting properties. For example, I start with V equals L and then force mass out of Cohen reals to make it easy. In the extension, I've got non-constructible reals like the Cohen real that I added. The set of non-constructible reals is ordinal definable. It's in this topos. None of its elements are, because no single non-constructible real is ordinal definable in that model. So you get non-empty objects in the topos that have no morphisms from one. even though this is basically a set theory setup. And even though it's a topos, so the internal logic works perfectly well, it sees things just as they really are in that Boolean extension. The internal logic is fine, but looking for actual morphism is unsuccessful. So those are just to give you some idea of the scope of the notion of topos beyond the ones that are actually involved in Gaunt's stuff. And now, back to Gaunt. Gaunt's local theorem. Okay, I want to have some notation so this doesn't get too long. I think it's too long already, but let's see what I can do about it. Okay, fix the topos E, fix a natural number N. I'm just going to write P. I think P is supposed to stand for point. PEN means if an object in E has exactly n elements, in the sense of the internal logic, then there is a morphism. Okay. I think the next thing here should be, what does that mean in the relevant topo? I have model of set theory over I, so I fix families in M. This just says choice set, because to have exactly n elements in the sense of the internal logic is to have n elements in M as an element of M. And to have a morphism from one is to have a choice function. So this P thing in that topos is just the choice axiom. On the other hand, if you take the same topos theoretic statement, interpret it in G sets where G is a fixed group, then it says whenever G acts on an n element set, it has a fixed point. Acting on an n set is this, and fixed points are these morphisms. So if I drag in one more piece of notation, as before, Z is a finite set of natural numbers, N is a natural number, Z arrow N in a topos means if you have this P idea, P principle in that topos for all the elements of Z, then you also have it for N. And with that, I can write down Gaunt's theorem in a topos version. This first bullet item, in view of what's up above, is just saying the local version of Z choice implies N choice. This implication holds, Z arrow N holds in all topoi of this form, when M is a model of set theory and Y is an element of it. And Gaunt's criterion for when that happens is the same statement, Z arrow N, now interpreted in this other batch of topoi, using G sets for a finite group. Now, what I want to do, finally, is get to one of my own theorems, which is mostly adding one more line to Gaunt's theorem. Okay, so this is nothing new. N is still a natural number, Z is still a finite set of natural numbers. Following are equivalent. The first one is the local version of the implication between finite choice principles. This is for each I individually, this implication holds, and we're saying that's provable in ZF. It doesn't matter whether you do ZF here or ZF with atoms, because there are enough transfer theorems to do it, thanks to, well, the effort so far originally, but we need extensions, at least one extension that maybe make it transfer atoms to the atom. So this is the original question about the local implications. Second bullet item is just Z arrow N, a topos interpretation of the first. The third bullet item is Gaunt's criterion, as on the previous slide. The new thing is, well, okay, so we've got one class of topoi here, M mod I type topoi. We have another another sort of topoi here. What other topoi might this sort of thing work in? And in some sense, here's the optimal result. Same property in all topoi, period. So there's, in that sense, the result spreads from these topoi, special ones, to all topoi. There's still the question of, could you spread from some other small class of topoi to all? I'm not going to say anything about that because I don't know very much about that. So this is the extension to all topoi of the local bound theorem. Here's the global one. For every n and z as before, this is now ZF proves the global implication. If you have Z choice for all index sets, then you have it for n. You have n choice for all index sets. This next bullet item is the transcription into topos form. Notice that the difference is, instead of having here something about this P holding in E for all elements of Z, it now has to hold in some additional models of the form E over F. So we're looking at index families, index by some finite object. This F is essentially the 6 things that I had in the original first group. 6 pairs or elements. This is the general version of that. Same thing in topoi of the form Z sets. Oh, I should have said something here. What's finite? I'm going to take time. Finite means k elements in the internal sense for some natural number k. And of course, likewise here. And then the equivalent is same story, except the topos doesn't have to be of this form, m over I, or set to the g. It's any topos. I snuck in the word decidable here, but with the definition of finite that I just gave you, decidable is redundant, you can leave it out. There are more popular definitions of finiteness in intuitionistic logic. If you use one of those, you have to go in decidable. So that's the general global theorem. And considering how long I've talked, there are a few more slides. They have something, they're sort of hand waving at the proof. But I think I've gone long enough and I will just stop there. Thank you.
Thank you.
Thanks very much, Andrew.
Okay, let me see if I can get this thing to shrink so that I can see somewhat more, a few more of you. Nope, that still does not work. Oh, well. I think that's because I'm the presenter. Oh, let's see, I could stop sharing, then I probably see everybody. Are there any questions that relate to stuff on the slides? Because I think if I stop sharing, then you can't see the slides, but I can see you, which makes me somewhat happier.
Right. Yeah, so are there any questions?
I have a question.
Okay.
So I mean, I kind of asked this before, but I'm going to ask it again now that I've seen the rest of the talk. So if that last theorem that you had, or a bunch of the theorems, so you have something about ZF proves, which is essentially a statement of arithmetic because you're talking about proving things, right. And you have things about finite groups. Right. If you instead of, I don't know if this is a topos, but if instead of looking at a model of ZF and modding out by this I, you take some model of PA and do the same thing, does the result go through?
The result goes, the theorem is fine, but the definitions are shot. So let me try and explain that. If you would, so first of all, if you want to work relative to PA, you should probably work in the universe of hereditary finite sets, so that you've got sets to deal with rather than funny numbers. Spoken like a true set theorist, I guess. Then, in that context, one of my early slides said, I'm going to always assume that there's a natural number object. Just sort of say, actually. So I have to cross that off of the slide. There's no natural number object anymore. And then I have to be somewhat more careful about what these n's, these natural numbers that I was throwing around, are. And that can be done without having a natural number object. We're always talking about some finite set C and some particular natural number n. So all of that can be done, but any attempt to quantify over those n's is now not going to be available. So I think I would have to fix up some definitions, but the theorems, the proofs of the theorems don't really need the axiom of infinity.
Okay, cool. Thank you very much.
See if, oh, I seem to have faded again.
So in order to prove that, to produce these counterexample models of ZF where these implications don't hold, is the method the usual symmetric submodel constructions, or?
Yeah, okay. What I'm about to say is true in all the cases that I remember, and I think it's in fact true in all cases, that the best way to do it is to first do it in a Minkowski model of atoms, where one can see where I can see what's going on, and then invoke transfer theorems that say that if you've got something working in a Minkowski model, you can get it in an honest CF model. In each case, so when you build models to violate these implications, what you have to do is, of course, make some choice from n element sets come out false, while choice from z element sets comes out true. In the local case, that's fairly easy. In every case, you violate it with the index set being omega, and you essentially do something like the second Frankel model, and it transfers extremely easily. When you want to do a global case, the granddaddy of all transfer theorems, the Yeh-Sofer theorem, will transfer the result that choice from n element sets fails, but transfer the result that choice from z element sets fails for all, that it holds for all index sets. That, as far as I can see, is not covered by the Yeh-Sofer theorem, but it is covered by some of the broader theorems that David proved in his thesis. I think they're all in his thesis. Unlike Pink, unlike Tarski, and unlike Gaunt, David's stuff is actually published. And I think his transfer theorems do cover things like choice from arbitrary size Z element sets.
Okay. Thank you. Any further questions? Okay, it seems we don't have any further questions. Thank you very much for this talk. It really makes me want to learn more about topos theory.
Have fun.
Okay, thanks a lot.